Welcome back, everyone. This is the second part of our third lecture, and again this lecture is on thermal conductivity of different materials. Now before we jump right in, I want to tell you the definition of porous composites. Now a porous composite is basically having pockets of air or liquid in a material. That's all it means. And the reason this is interesting for us is because let's say we have a block of wood, but this block of wood hypothetically has a bunch of pockets of air or a bunch of pockets of liquid. Now, the thermal conductivity of this composite as opposed to the thermal conductivity of your conventional 100% wood block is a lot different. So we need to investigate different ways of approximating the thermal conductivity when we have our porous composite. Now, just to reiterate, I do not have the capabilities to type or really write in these screencasts, so write down this definition of porous composite. It means when you have pockets of air or a fluid in a material. Now, let's start off with the Russell equation. Now, the Russell equation is another way of finding the thermal conductivity of a composite using the thermal conductivity of our pure solid. So in the wood example, the thermal conductivity of the solid would just be 100% pure wood, while the thermal conductivity of the composite would be the wood with the pockets of air or the liquid. So this is the general equation. We have this squiggly, which I don't know what to call it, and that is basically a ratio of the thermal conductivity of the pore, i.e., what is the pore? That is, in our example, the pocket of air or liquid in the wood over the thermal conductivity of our 100% pure solid. Now, this is simply a ratio, and we need it for the sake of the equation. Now, what is the other unknown in this situation? It is P, porosity, which is the volume of one pore. So the volume of one pocket of air or one pocket of liquid over the volume of the entire composite. Now the volume, and sorry that the word composite kind of got scratched off there. It was hard to capture this entire page into one screencast. Now, let's take an applied example with one-dimensional heat conduction. Now, let's first break this problem down. What do we actually think of when we think of one-dimensional heat conduction? One-dimensional heat conduction means that we assume that the system that we're dealing with is in one, like it is basically like a line, because three-dimensional is like a block, two-dimensional is like a plane, and one-dimensional is essentially a line. So and the reason we're working with one-dimensional heat conduction as opposed to two-dimensional or three-dimensional is simply for the reason of avoiding complexity, because we need to nail down the core concept. Now, Q, which we defined earlier as heat transferred, and Q hat is Q over the area, we're defining it for only one component. Now, Qx this is the equation, right? Has only one component, and this is our temperature gradient. Now, in our one dimension, we're assuming a flat wall. Now, you might say, wait, Sahib, this contradicts what you said earlier when you said that two-dimensional is like a plane and one-dimensional is like a line. I still stand by my words. The reason we are defining it as a flat wall, which ultimately is considered to be like a plane, is because we have one dimension in which the actual composite is varying, that is called x over here, but our second dimension that we're considering, which is independent of, like, in terms of like what we're talking about of x, is temperature T. Now, of course, temperature T varies with x, but in this one-dimensional case, we're talking about x, and T acts as a second part of the wall. Or, yeah, exactly, a second part of the wall. Now, we're going to be measuring how heat is transferred from point 0, x equals 0, to point x equals L through the wall. Now we're going to definitely have different temperatures at x equals 0 and different temperatures at x equals L. So that is why we have T1 for x equals 0 and T2 for x equals L. Now over here, this is a small differential area. Sorry, let me just highlight that over here because I kind of blocked it out. Small differential. Now going back. So the reason this is a very important part, steady state. Now what does steady state mean? Steady state means there's no accumulation term, meaning whatever heat comes in over here, that same quantity of heat leaves over here. So heat in equals heat out, hence steady state, right? So yeah, the heat inside at when x is equal to 0 plus x plus delta x, which is the small cross section that we spoke about, are equal to each other. Q is the same across the entirety of this plane or line, quote unquote. Now, let's jump over here. Now, this is basically reiterating the same thing, no accumulation term, meaning there is no change in Q across X. Like we said, steady state, that is all it means, and it is redefined over here as the limit. Now, all of this stuff over here, let me put some green in there. All of this stuff over here is saying literally the exact same thing. Steady state means no heat accumulated. Heat does not change across across X. Now, I know I said this a billion times. I just need to really emphasize it because this is a huge concept when dealing with heat and mass transfer, because this assumption is crucial for beginning problems. Again, Q hat is equal to Qx over A, and that is constant throughout. And the Q hat basically just means, like we defined over here, with Q basically means the rate is constant, right? Again, yep, as said over here, the rate is constant. Now, what are we trying to find over here? Now, what we want to find over here is we actually want to solve for what is Qx? Like, I know that Sahib, you're telling me that it is constant. It is this quantity of heat that does not change. But how do we actually calculate it? I want to understand how it is calculated. Now, this is actually a very simple differentiation problem. You have your differential over here that you can easily set up to solve for your Qx. Now, looking over here, this is obviously an arrow. I know my handwriting is disgusting. This is very messy, but you'll have to deal with it, unfortunately. So, we're moving from temperature 1 to temperature 2, i.e. we're moving from point 1 to point 2. We're taking our temperature differential, and you might be asking, where did this equation come from? If you rearrange this equation over here, you get this equation over here, right? That's obvious. If not, please review some calculus or put a message in the comments, and I'll explain that. You have this differential over here, and all you're doing is essentially solving for it. Now, you might be asking, why is it T1 minus T2? The reason for it not being T2 minus T1 is because we literally just took this minus over here and divided it by this. And the reason we have a minus over here is because heat is leaving the system. It's going from one place to the other. It's not going in. And yes, we essentially solve for Q over here. And once we solve for Q, we can also solve for K using the same equation, actually, and that is all. If you are annoyed by all these markings, as I definitely would be if I were a student, just replay back to the beginning of the video and copy down the notes. Thank you very much for listening. Have a nice night.